You are in a supermarket, you buy an apple and 2 bananas and it costs you $3. You see another customer who has bought 2 apples and a banana and he pays $4. You're a kind of person who just buys things without checking the price tags, but you suddenly just wonder how much each item costs, because you have realized that apples must be more expensive than bananas. If we represent the price of apples by x1 and the price of bananas by x2, the total cost by b1 and b2, and these coefficients by these 4 elements, we are dealing with a system of linear equations. To solve this specific example of apples and bananas, we can multiply the first equation by -2 and add the 2 equations, which makes the price of apples disappear, and we find the price of bananas to be about 66 cents. And using the first equation, knowing the price of bananas, we can find the price of an apple to be about 166. There is also another way we can solve this problem. By writing one of the unknowns in terms of the others, we can write these 2 equations. They can be represented geometrically by 2 lines on a 2D plane. By setting x1 to 1, we get 1 for x2, and also by setting x1 to be -1, we get x2 to be 2. At this point, you might ask, how can the price of apples be negative? The thing is that we are using a mathematical representation to tackle a real problem. And at this point, we are looking for a pair of points that exists on this 2D plane and explains the prices of apples and bananas. So, we are using an abstract framework which can also be represented geometrically, and that is great because it intuitively helps us. These are the 2 points we found, and by connecting them, we have a line that represents all the possible ordered pairs that can be shown by the first equation. For the second equation, we choose 2 other points, for one of which the price of banana gives 0. It's free, just joking. Again, we are abstractly thinking about all the possible numbers in the set of all real numbers. So these are the 2 points, and if we connect them, we will get another set of real numbers presented geometrically that are all the possible solutions for the second equation. We know that this intersection is where things get real. These 2 numbers can represent the prices in real life. So we had a real life problem. We used a mathematical framework to look at the problem in an abstract way. We used some methods to find a solution in this framework, and now we can have real-life interpretations of the solutions based on the given answers. So you might ask, what if the 2 lines never intersect? What would be the interpretation? To answer this question, this form of writing the linear equation can help. In a set of x1 and x2, we have x and y, and m is the slope of each line. B is also intersection point with the vertical axis. So, these are the 2 sets of solutions to our linear equations presented geometrically. Both of the lines have the same slope, but the intercepts are different. But what does it mean? It means that the salesperson in the supermarket is selling the same items at different prices, which is open to different human interpretations. Maybe a mistake, maybe something more. You might ask, what if the 2 lines align in the same direction and have infinite intersections? What is the interpretation in this case? In this case, both of the lines can be represented by the same equation. In other words, you have bought an apple and 2 bananas, and the other customer has bought the same proportion of the same fruits. So we just have to ask the salesperson how much each item costs, because we don't have enough data to figure it out by this mathematical model. So if we have a number of unknowns or variables with the coefficients that are represented by a and 2 indices, for which the second index is associated with the number of x, and also we have m numbers which are represented by b, and their corresponding index in a is the first index, we are dealing with a system of linear equations. And the answer to this linear equation is an n-tuple, which can be represented by real numbers in an n-dimensional space. Now let's take a look at some 3-dimensional cases for which we have 3 unknowns. In this example, the sum of the 3 variables gives different outcomes which show that they have no intersections. Geometrically speaking, there are two parallel planes in the 3D Euclidean space that have no intersections. And the third equation is another plane that has intersections with these two planes separately. For this set of equations, which also can be represented by three planes in a 3D space, there is a single point at which they intersect, and the system of linear equations has a unique solution. In this example, the second equation is exactly the first one but multiplied by 2, so they show the same plane. As x1 and x2 are equal, we can eliminate one of the variables and reduce it to this system, which is a representation of a line. So in this example, there are infinite answers that lie on this line. In this last example, the second and the third lines are multiples of the first line, so they are all the same plane. And the intersection is all the points on a plane which is represented by one of these equations. By looking at the linear equations we have, you can see that both sides of the equation can be arranged into a column matrix. Another form of writing these equations using column matrices is to multiply each column matrix of the coefficients of the unknowns and adding them. So for each unknown, we have a column matrix as the coefficient that includes all the coefficients for the corresponding variable. And obviously, on the other side of the equation, we have another m by 1 column matrix that includes b's. We can also multiply two matrices with different dimensions to get the same outcome, which is a column matrix. On the left, we have an m by m matrix that is multiplied by an n by 1 matrix, and the result is an m by 1 matrix. In the next video, we are going to learn more about matrices to see how we can use their properties to solve these kinds of equations and maybe more.